In this lecture, we look at symmetries of functions. We examine even and odd functions. A symmetry of a function is a transformation that leaves the graph unchanged. Let's look at the functions below. On the right, it's a graph of y equals x squared, and on the left is a graph of the absolute value function. Both graphs allow us to view the y-axis as a mirror. A reflection across the y-axis leaves the graph unchanged. This reflection is an example of a symmetry. A symmetry of a function can be represented by an algebraic statement. A reflection across the y-axis interchanges positive x values with negative x values, swapping x and minus x. So for these functions, f of minus x is the same as f of x. The statement for all real numbers x, f of minus x equals f of x, is equivalent to the statement. The graph of the function is unchanged by reflection across the y-axis. What other symmetries might a function have? We can reflect the graph about the x-axis by replacing f of x by minus f of x. But could a graph be fixed by this reflection? Whenever a number is equal to its negative, then the number is equal to 0. X equals minus x implies that 2x is 0, which implies x is 0. So if f of x was minus f of x, then f of x would have to be 0. But we could reflect the graph first across one axis and then across the other and still have a function. Reflecting a graph across the y-axis and then across the x-axis is equivalent to rotating the graph 180 degrees about the origin. When this happens, f of x is equal to the negative of f of negative x. F of x is equal to minus f of minus x. If f of x is equal to minus f of minus x, then we have rotational symmetry about the origin. In this case, we may multiply both sides of that equation by minus 1 and rewrite our equation as f of minus x is equal to minus f of x. So far, we have discussed two types of symmetries for graphs of functions. Reflection symmetry about the y-axis, in which case f of minus x is f of x. Rotation symmetry about the origin, in which case f of minus x is minus f of x. In both cases, notice that we're plugging in minus x, making a computation, and discovering that that's equal to either f of x or minus f of x. We note that functions like f of x equals x squared and f of x equals x to the fourth, where the exponent on x is even, will always have the property that f of minus x is f of x, since minus 1 to an even power is equal to 1. Similarly, functions like f of x is x, f of x is x cubed, and f of x is x to the fifth, where the exponent on x is odd, will have the property that f of minus x is minus f of x, since the minus 1 in the negative x will be raised to an odd power, and minus 1 to an odd power is equal to minus 1. So this motivates the following definitions. A function f of x is even if f of minus x is f of x, and it's odd if f of minus x is minus f of x. An even function has reflection symmetry about the y-axis, and an odd function has rotational symmetry about the origin. We can decide algebraically, without looking at the graph, if a function is even, odd, or neither, by replacing x by minus x and then computing f of minus x. If we get f of x as our answer, the function is even. If we get minus f of x as our answer, the function is odd. And if we get neither of those, then the function could be neither even nor odd. The graphs of a variety of functions are given below on this page and the next. Consider the symmetry just by looking at the graph, and decide from the graph drawings if f of x is odd, even, or neither. The graph on the left has reflective symmetry about the y-axis, so it's even. The graph on the right has rotational symmetry about the origin, so it's odd. The graph on the left has reflective symmetry about the y-axis, so it's even. The graph on the right has rotational symmetry about the origin, so it's odd. The graph on the left here If we rotate that picture about the origin, we get the same graph back. So we have an odd function, and the same thing on the graph on the right, rotational symmetry about the origin. The graph on the left has reflective symmetry about the y-axis, so it must be even. The graph on the right now has rotational symmetry about the origin, so it must be odd. The graph on the left, rotational symmetry about the origin. The graph on the right, reflective symmetry about the y-axis. The graph on the left is odd. The graph on the right is even. Let's do some algebra without necessarily worrying about the graph. Consider the function f of x equals x cubed minus 4x and decide if the function is even, odd, or neither. Now if we look at the picture, the function is odd since it's symmetric about the origin. Here's the graph of it. But we could check this out algebraically. At the bottom of the screen we're going to compute f of minus x. Let's insert minus x into the function. So everywhere we saw an x we write down minus x. And so we get minus x cubed minus 4 times minus x. That's the same as minus x cubed plus 4x. And that's just the negative of the original function value. So by algebraic computation this function is odd. Here's another function. F of x is x divided by 1 plus x squared. Even, odd, or neither. We can compute f of minus x. Replacing x by minus x, we get minus x in the numerator. The denominator becomes 1 plus the quantity minus x squared. Since minus x, the quantity squared, is x squared, we can simplify the denominator. And so we get minus x over 1 plus x squared, which is the same as minus 1 times x over 1 plus x squared. And so we're getting minus f of x. Since f of minus x is minus f of x, this function is odd. One more. F of x is this expression. Let's decide if this is even, odd, or neither. Given my function, I can plug in minus x for x. I have minus x to the 5th power plus 7 times the quantity minus x squared minus 3 times minus x plus 5. Simplify my algebra a little bit. I have minus x to the 5th plus 7x squared plus 3x plus 5. F of minus x gives me that expression. Is that the original expression? No, it's not. Is it the negative of the original expression? In this case, it's not that either. It's neither equal to f of x, nor it's equal to minus f of x, so it's neither even nor odd. Just as a curiosity to toss out there, there is a function which is both even and odd. What is it?